The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
We're back here for some more stimulating discussion of chemistry. And I want to begin today by just saying that I find it particularly ironic that on the day that I'm all prepared to speak to you about the molecular orbital energy levels of polyatomic molecules, for which I'm using methane as an interesting example, the boards are screwed up. Okay, this is the reason for that apparently is that this screen came down and won't go back up. And one of the reasons that I've designed my presentation technique for you this semester so heavily around the use of the blackboard is that last year when I taught the class, I had a lot of feedback from students about how the one day when we had audio-visual problems and I couldn't use my PowerPoint and instead gave an impromptu chalk talk, that was their favorite lecture. And that was this polyatomic lecture. Okay, so maybe next year we'll be entirely back to PowerPoint. I don't know. We'll see. But fortunately, I did write out my notes this morning in electronic format so I can make use of them on the sideboards. And in addition, I want to display for you some molecular orbital shapes and properties. And I will do that by starting out. Actually, I would like to start, if I could, with this one. We'll go back to the document camera in a moment. By starting out right where we left off last time, you'll recall that we were looking at diatomic molecules. So we started out with a 7-orbital problem 2 lectures ago. We looked at the planar BH3 molecule. So we had a molecule where the MOs were mixing in 2 dimensions. And then last time when we looked at homonuclear and heteronuclear diatomic molecules, the MOs were in fact mixing in just along an axis in 1 dimension. And so when we left the situation last time, we had arrived at some kind of an understanding of the energy levels in the carbon monoxide molecule. And these were being developed especially with reference to CO being a poisonous molecule, whereas N2, another 10 valence electron diatomic molecule, is very, very inert. So why was that? And it turns out that you have the very electronegative oxygen atom on the one side of the diagram with its very low energetically lying orbitals, mixing with the carbon orbitals that are higher in energy. And the neat thing about this for the carbon monoxide molecule is that it results in an asymmetry of the molecular orbitals, because the coefficients are not the same on the carbon side as they are on the oxygen side, as those atomic orbitals blend together into the 4 sigma and 4 pi molecular orbitals that we have. We have a total of 8 MOs, and they distribute energetically as 4 energy levels in ascending energy that are sigma in symmetry, that is cylindrically symmetric about the internuclear axis. And then we had 4 that are pi, 2 energies, a pi bonding with 4 electrons and a pi anti-bonding with just virtual empty orbitals. And because this highest occupied molecular orbital of carbon monoxide is so heavily concentrated on the carbon end of the molecule, when you can essentially view this as a carbon-based lone pair. It's got this big lobe here through which the carbon can serve as a nucleophile or as a base and bind to something that has an empty orbital. And if that something that has an empty orbital also has a filled orbital that matches the symmetry of the LUMO of carbon monoxide, then you get the possibility for multiple bonding between the carbon of the CO molecule and that other entity. And we will see that that other entity may in fact be a D-block transition element such as iron. And what I wanted to do was to go ahead and show you that the LUMO is an interesting and unsymmetrical one as well. So let's take a look at that. And so in this picture, I've gone ahead and included a little ball and stick diagram underneath the representation of the orbital lobes. So here's the carbon, and the oxygen is colored red. And you can see that the lobes on the LUMO, the lowest unoccupied molecular orbital in this system, are also large on carbon relative to oxygen, the same as we had found for the highest occupied MO. So what this means is that that carbon atom in the CO molecule is simultaneously a base in the sigma system, and because this is our lowest unoccupied molecular orbital, our carbon atom is actually an acid in the pi system. And that makes it electronically very complementary to d block elements, as we'll see when we get into the chemistry of elements that do have valence d orbitals in addition to s and p, coming up in a couple of lectures. And so what can happen is that, let's say that a carbon monoxide molecule somehow erroneously finds its way into your bloodstream. You have their hemoglobin, which acts, the iron atom at the center of which acts reversibly to bind the dioxygen molecule, but it irreversibly binds to the carbon monoxide molecule because the iron center, which is sitting at the center of a heme unit, as I mentioned, and we'll talk about the structure of hemoglobin and the way that it functions a little bit later. But if CO gets in there, it binds to the iron through the HOMO, acting as a base, to the metal, acting as a sigma acid, and also through d electrons being able to act as a pi base from the metal, binding with this LUMO of the carbon monoxide molecule. And this LUMO is doubly degenerate. That means there's two of them at the same energy. And we'll come back to this issue of orbital degeneracy later in today's lecture. But that asymmetry, electronic asymmetry of carbon monoxide, and the fact that the HOMO and LUMO are both centered on the carbon end of the molecule are what makes CO such an interesting molecule and such a reactive molecule, and therefore a poison. And so now let us please go back to the document camera. What I have shown here are the 5 platonic solids. Actually, I spent a lot of time over the weekend practicing drawing these on the chalkboard so that I would be able to do that very nicely for you. And here it comes that we don't have that option today. So I'll show them to you this way. And the platonic solids are the 5 regular polyhedra. And that means that they're polyhedra that have as their faces regular polygons that are all identical. And the reason I'm bringing this up today is that we had talked about issues of symmetry with reference to molecular orbital theory. And these are all very highly symmetric shapes, as you can immediately recognize. The buckyball that we looked at earlier is not here because it has both 5-membered rings and 6-membered rings on the faces. And so it doesn't have all the faces identical, and those that do have all the faces identical are the platonic solids, and the complete list of those is shown here. With triangles, you can put 4 of the equilateral triangles, you can put 4 of them together to make a tetrahedron. Okay? There's actually a journal called Tetrahedron, and there's another one called Tetrahedron Letters, and there's another one called Tetrahedron Reports. And the reason is that organic chemistry is carbon-based, and carbon so often gets involved in forming tetrahedra. And so the tetrahedron is a very important symbol of organic chemistry. We'll get back to that. And then with triangles, if instead of putting 4 of them together, you put 8 of them together this way, you get the octahedron. And the octahedron is equally important as a symbol for inorganic chemistry. And the reason for that is that when we have metal ions in solution, they often sit at the center of a coordination octahedron in which 6 ligands bind to that metal center. And we're going to get into how that was discovered pretty shortly by Alfred Werner, another Nobel laureate in chemistry. And with triangles, you can also make the icosahedron shown here, and this has 20 faces. Okay? And the icosahedron is important in chemistry, and certain elements, for example, boron, actually have structures in the solid state in which the boron atoms are arranged at the vertices of a regular icosahedron. So this is a chemically important shape as well. And then if you go from triangles to squares, you can of course make a cube, and probably the most familiar of the platonic solids to us. And then if we go up to pentagons and we put those together, as you can see here, we can put 12 pentagons together in a regular way that gives rise to what we call the pentagonal dodecahedron. And you can imagine that each of these vertices could be a CH unit, carbon-hydrogen. And then each carbon would have its valence of 4 satisfied, and there would be all single bonds at the perimeter of this round molecule. And in fact, that dodecahedron molecule was the objective of organic synthesis for quite a long time before it was finally successfully synthesized by Leo Paquette. Okay, so you'd be surprised at the kinds of challenges maybe sometimes that do drive chemists to do what they do. And that's the platonic solids. I'm going to be focusing our attention on methane. And if I could have the sideboard go back to the computer for a moment. Be great. Okay, so these are the notes for today's lecture that I wrote up this morning that you'll be able to download later today, or maybe you already can, I don't know. In any event, when we approach the methane problem in molecular orbital theory, what we do is we recognize that the tetrahedron can be conveniently inscribed into a cube by placing hydrogens at alternating corners of the cube as shown here. And then when we do that, the carbon atom of the methane molecule lies at the very center of this cube. And this way of arranging the system in space will help us to simplify the problem of the molecular orbital energy levels for the methane molecule. Okay, and we're going to be ultimately working toward a comparison of the molecular orbital description of the methane molecule with that afforded by valence bond theory. Now, some of you approached me after lecture last time and said, well, what happened to hybridization? And if you wanted to talk about the methane molecule in the language of valence bond theory, you would say that this carbon atom is sp3 hybridized in order that it may form simultaneously 4 2-electron bonds between the central carbon and the 4 peripheral hydrogens. Well, where hybridization went is it stayed with valence bond theory. Okay, so let me re-emphasize the distinction between the molecular orbital treatment of molecular electronic structure as contrasted with the valence bond theory in which hybridization plays a role. It does not play a role in the language of MO theory, so please keep those quite distinct. And now we need to choose a coordinate system for our problem. And I won't spend too much time discussing how we choose the coordinate system, but what we've done in the present case with methane is to choose the x, y, and z axes each to come out of the faces of the cube. And we do this because that choice of coordinate system will lead to the equivalence of the carbon's 2px, 2py, and 2pz orbitals in 3D space. We could choose a different coordinate system, and that would make the problem more difficult. So what we've done is chosen a convenient set of coordinates where the x, y, and z axes each come out of the faces of our cube. And now we recognize that the methane problem, like the homonuclear and heteronuclear diatomic molecule problems we talked about last time, is an 8-orbital problem. Okay, the diatomics N2 and CO each had 10 electrons to go into their 8 molecular orbitals. And here with methane, we have 8 electrons, 4 coming in as the valence orbitals from the carbon atom, valence electrons from the carbon atom, rather, and 4 coming in as the 4 valence 1s electrons for the 4 hydrogens. And our 8 orbitals are the carbon's 2s, 2px, 2py, and 2pz orbitals. And we have 4 more orbitals, the 1s from each of the 4 hydrogens. So we know how many electrons are going to be able to go into our MO energy level diagram. We know how many MOs we're going to have because we know how many valence AOs we have. And those numbers are equal at 8. So the choice of this problem is predicated on my desire to show you how things progress as we go from a planar system to a linear system to now a system that has molecular orbitals that stretch out in 3-dimensional space. Okay? And so now we're going to take the following approach. We're going to say, how can we generate linear combinations of the 4 hydrogen 1s orbitals that will be so constructed as to match the nodal properties of the carbon atomic orbitals that are the valence orbitals of that carbon. Okay, so that is our goal and that's our strategy. And let me say also that in this tetrahedral symmetry, you can recognize that you can't distinguish any one of the 4 vertices of a tetrahedron from the other 3. And that's important. And that's also true from the way that we've decided to situate the hydrogen nuclei on this cube relative to our coordinate system. In other words, none of these 4 hydrogens lie on any of the 3 Cartesian axes, right? And their relationship to the coordinate system and to the shape of the cube, each is indistinguishable from that of the other 3 hydrogens. Okay, and that's an important aspect of the way that we set up the problem. And why do I mention that? Because I mentioned that when constructing MOs in general, one of the first things you can do if you're going to be able to take advantage of symmetry to help you solve the problem of these MO energy levels and how they're constructed from linear combinations of atomic orbitals is to identify symmetry-related sets of atoms and orbitals. Okay? So if you're keeping that in mind, you'll realize that we're treating all 4 hydrogens together because they are indistinguishable from one another in the tetrahedral shape of the methane molecule. Okay, so that's important. If we had a more complicated molecule, such as if we were looking at, I get to use a little bit of board space today. Here's a slightly more complicated hydrocarbon molecule. And in a molecule like this is cyclohexane drawn in a chair conformation. Sir Derek Barton actually was the Nobel laureate who got his prize for discussing conformational aspects of hydrocarbons. We would find that the hydrogens split up into 2 sets. They're not all equivalent in the cyclohexane molecule in this frozen out chair conformation because we have one type that is equatorial and one type that's axial on each of these carbons as we go around the 6-membered ring. And so there's different sets that we would have to treat separately. But methane is more symmetrical, and all 4 hydrogens in the methane molecule are identical, so we're going to treat them together in developing our linear combinations. And coming back to this, what we're going to do, once again, to generate these things, is to imagine the central atom atomic orbital as growing out in space, out to where the hydrogen nuclei are, and then we're going to take the sign of the wave function that we find out there and apply it to those hydrogens that are out there in space in order to see what our linear combination must look like. So if you imagine the carbon 2s orbital, which has the same sign, positive everywhere, and imagine it growing out to where the hydrogens are, and we're labeling the hydrogens A, B, C, and D as shown here, and we'll keep that same labeling scheme throughout the development of this problem, you would see that the carbon 2s positive wave function as we imagine it growing out to where the hydrogens are, would touch each of these hydrogens at the same time, and thus we confer the sign positive on all four of the contributors to this first of our linear combinations. And what that will represent is simultaneous bonding of the carbon 2s orbital with all four hydrogens, and with the same sign everywhere. And so we can write down 1/2 A plus B plus Z plus D, where I'm using A here to represent the hydrogen 1s orbital associated with hydrogen labeled A. Okay, so I've just abbreviated that into A. And similarly, B is the hydrogen 1s orbital associated with hydrogen B, and so on. So this is a linear combination of these four hydrogen orbitals, and it's normalized with a half here. And we have the same coefficient on each of the four hydrogens, so the size of the lobe that you would draw at each four of these positions would be the same. And that's number one. So we've built a linear combination based on the nodal properties of the carbon 2s atomic orbital. And now let's do two more. And we're going to base these on the nodal properties of the central carbon 2px orbital and the central carbon 2py orbital. I'm using the same coordinate system as I started with, namely that the positive x-axis comes out of the face of the cube and comes toward us, and the positive y-axis comes out of this face of the cube and goes that way. Okay, and we'll look at z in a moment. That one is going straight up out of the top face of the cube for positive z. So what you can see is that if you imagine the carbon 2px atomic orbital as just growing out to where the four hydrogens are, we'll see that hydrogens in positions A and B will experience the positive lobe of the carbon 2px orbital at the same moment as the two hydrogens in back labeled C and D experience the negative lobe of the carbon 2px orbital. And so we give positive phase to A and B and negative phase to C and D, and we give them the same coefficient everywhere, such that this linear combination is normalized as 1/2 A plus B minus C minus D. Okay, so that's our second linear combination of hydrogen orbitals, and this one has been so generated as to match the nodal property of the carbon 2px orbital, the key feature of which is that it's everywhere positive along positive x, and everywhere along negative x, it is negative. And the 2py orbital of carbon has the property that everywhere in the plus y region of space, it's positive, so that C and B will be associated with a positive sign for this linear combination, and the 2py orbital is negative everywhere along negative y back here, and that's where hydrogens A and D are located, so A and D will carry a negative sign for this new linear combination, which is 1/2 of minus A plus B plus C minus D. So this is just one way of writing down the picture that we see here. And there's only one left to be generated from the nodal properties of the carbon 2pz orbital, which has its positive lobe oriented along positive z and its negative lobe oriented along negative z, and it has the xy plane as a nodal surface. And so therefore, hydrogens A and C will carry a positive sign because they are oriented and located in the plus z region of space, whereas hydrogens B and D are located in the negative z region of space, so they will carry a negative sign. And that one can be normalized also with normalization coefficient of 1/2. And so it's A minus B plus C minus D. And just don't forget that these letters refer to the 1s orbitals associated with the hydrogens that are so labeled. And we started with identifying the fact that the four hydrogens in this problem are all equivalent, and thus their 1s orbitals are all equivalent, indistinguishable from each other with respect to their spatial orientation. And so we took four atomic orbitals and we are constructing from them 4 linear combinations of those 4 atomic orbitals. And I want to emphasize what I've written here, which is that with the coordinate system we've chosen, and in this high tetrahedral symmetry, the carbon's 2px, y, and z orbitals are identical, and just like in a carbon atom floating free in space, they're degenerate. And that means they have the same energy. Okay? And so we'll talk about orbitals in atoms being degenerate in a moment, but we find that the 2px, y, and z orbitals on that carbon are going to have the same energy, and they're degenerate. And the molecular orbitals constructed from them in this tetrahedral system will have the same property. They will be degenerate. So this something that is occasionally associated with high symmetry is multiple MO degeneracy. Okay. So next, knowing what our carbon atom atomic orbitals are, and knowing also what our 4 linear combinations are of the hydrogen 1s orbitals, we can now allow them to interact in ways that are either bonding or anti-bonding. And they interact, of course, according to their nodal properties. Those linear combinations that have the same nodal properties as a particular carbon atom atomic orbital will lead to a bonding interaction and an anti-bonding interaction. And we have an 8 orbital problem, so we better see 8 energy levels appearing in our molecular orbital energy level diagram for this methane molecule. And when we go down here, starting at the lowest energy molecular orbital, we find that it can be constructed by adding to the carbon 2s orbital, which is, once again, spherically symmetric, this linear combination that is A plus B plus C plus D. And we can draw this with a surface like this, which envelops all 5 of our nuclei, and which has the same sign everywhere. And so our lowest lying molecular orbital, our most bonding molecular orbital, our most stabilized MO, which can house a pair of electrons because it is singly degenerate, is one that will look something like this. It envelops all 5 of our nuclei with this, and effectively, the pair of electrons is associated simultaneously with all 5 nuclei, and the wave function has the same sign everywhere, just like the carbon 2s orbital, from which this is partially constructed, does. And then next, we have 3 molecular orbitals that are each built by forming bonding interactions with the carbon's p orbitals, px, py, and pz, with the set of linear combination that matches that carbon orbital in terms of the nodal properties. And we built them that way, so that becomes particularly straightforward. This one here, it's coming out the face that points to the right, and so you can see that this one is based on the carbon 2py orbital. And if that carbon 2py orbital makes a bonding interaction with the linear combination denoted as minus A plus B plus C minus D, the bonding interaction here is signified by this plus sign. So we have a plus sign here and a plus sign here. And thus, we have a molecular orbital that has the same nodal properties as a carbon 2py orbital does, which means that the xz plane is a nodal surface for this molecular orbital. And what it looks like is kind of a 2-bladed propeller. You have a plus phase that's distributed enveloping the 2 hydrogens that we labeled B and C, along with that positive lobe of the carbon 2py orbital, so that you have that forming one blade of our 2-bladed propeller, and the blade with the other sign is rotated relative to the first by 45 degrees. Sorry, by 90 degrees, in fact, and will involve the distribution of bonding character over carbon's negative 2py lobe interacting with these 2 hydrogens back here, which are hydrogens A and D. And so we'll visualize these in a moment to make that more clear. But these 3 bonds, one oriented along X, one oriented along Y, and one oriented along Z, all look exactly like this. They're just rotated 90 degrees to each other in space, just like the x, y, and z Cartesian axes are. Okay, so I've only drawn one of them, but we have three of them because there is a threefold orbital degeneracy in this molecular orbital. Okay, so singly degenerate, then triply degenerate. And then as we go up in energy, we will find that our lowest unoccupied molecular orbital is constructed by subtracting. So it's the same as what I've written here, but with a minus sign. The C2s subtracting A plus B plus C plus D. So A, B, C, and D hydrogens all have the same sign to their wave function as each other, but they have the opposite sign as the contribution from the carbon 2s orbital to this molecular orbital. And what that results in is, as I've tried to indicate with some red dashes here, is that you generate a nodal surface in between the carbon and hydrogen nuclei that will go completely around and will intersect perpendicular to each of these carbon-hydrogen internuclear vectors. Okay? So you have a change of sign as you're traversing the path from carbon to any one of the 4 hydrogen nuclei. And that's what we get by just reversing the sign relative to the bonding counterpart of that orbital. And that makes this one anti-bonding. So we'll give it an asterisk here to denote anti-bonding character to this molecular orbital. And now, ascending in energy, we'll find that for each one of these orbitals that is bonding and oriented with respect to x, y, or z in Cartesian space, we find that there is an anti-bonding counterpart. And again, what we're doing is we're taking, for example, carbons 2py and subtracting the linear combination that corresponds to carbon 2py in terms of its nodal symmetry properties. So we're subtracting minus A plus B plus C minus D. So the carbon 2py has the same its positive lobe is oriented along positive y just as it is down here. But now we've reversed the sign of the 4 hydrogens. And what this introduces will be anti-bonding nodal surfaces in between the carbon and the hydrogens, and they are strong anti-bonding interactions because of the good directional overlap of say, the positive lobe of carbons 2py with these s orbital contributions in the negative from hydrogens C and B here, and back here A and D, rotated, of course, by 90 degrees. So one of the points that I was illustrating last time and really trying to emphasize in the context of MO theory is that in general, we expect orbitals to be higher in energy if they have more internuclear nodes. And the energy of the orbitals is also affected by which atomic orbitals are close to the MO in energy, and also by factors of overlap. And normally, for example, a sigma bond is typically associated with greater overlap than a pi bond because of the directionality of the overlap. And here you have an interesting case where this p orbital is not directed right at the hydrogen, and it's not a pi bond either. It's something in between sort of a sigma and a pi type of orientation. It's sort of an oblique interaction of the hydrogen 1s wave function with that lobe of the p orbital. So, but still, it gives rise to a very good overlap down here, and consequently a very strong anti-bonding character up here in the counterpart. And from calculation, this is the order of the energy levels that come out of that. And so we have only 4 energy levels, 2 of which are triply degenerate, so that we indeed have 8 wave functions that correspond to the molecular orbitals of this system. Question down here.
Why is it not negative 1/2 on the top anti-bonding orbital?
Could you just please say that louder?
Why is it not negative 1/2? Why is it just negative?
Okay, I can't really. Why did this not have the 1/2? The 1/2 is missing there because I forgot to put it there. Yes, to be normalized, it should have a 1/2 there. That's right. But then there's a further point that brings up, which is the following: that what I'm implying here is that there's equal amounts of carbon 2s in the bonding orbital and as in the antibonding counterpart, but that need not be the case. It could be that this is 0.6 here and that this is 0.4 up here, okay? And that is a greater level of detail than I'm really interested in going into for the purposes of this problem. But your point with respect to the coefficient is well taken. Thanks. Christine, maybe we can fix that on the one that gets posted on the web. So let's now look at these things using our VMD program. Starting from the lowest energy, and we'll work our way up. Okay, so which orbital is this? This is a molecular orbital of the methane molecule. One way you can identify orbitals is with where they are with reference to the HOMO or the LUMO. In this case, the HOMO is triply degenerate, and there's one orbital lower in energy than the HOMO. That's the HOMO. This would be then the HOMO minus 1, okay? Because it's one below the HOMO in energy. Okay, that's the one which is the carbon 2s plus A plus B plus C plus D. That's that MO there. Now, actually, let's go ahead and take that one away. Sorry about that. Let's see if you can figure out which one is this. So in order to figure out which one it is, you need to be able to realize where the nuclei are and where your internuclear nodes are, if any, and if so, how many. Okay. This is one of our hydrogen contributions. Here's a hydrogen contribution with opposite sign. Okay. And there's a piece of our carbon 2p orbital in the center. Now this is just one of three identical counterparts that are rotated 90 degrees with respect to each other in space. So I'm not going to show you all three of them. They all look exactly the same. Is this one bonding or anti-bonding? Yeah, this one's anti-bonding. And it does not have the same sign on all the hydrogens, so it has to be part of our LUMO, which is triply degenerate and involves bonding or anti-bond, in this case, anti-bonding between a carbon 2p orbital with a linear combination of 4 hydrogens. So you can see that when you have an anti-bonding orbital, you're depleting the electron density in the space between the nuclei rather than increasing it as you do in a bonding orbital. So let's go ahead and look at the bonding counterpart of this one. And we'll do that. Let's delete it. One thing that you will get, if you haven't already gotten it, is you're going to get a link to be able to download all the files that I use to show you molecular orbitals with in class. Because this program I'm using, this VMD program, is available on Athena, and you can also download it yourself for free onto your own computer if you want to. And so this is going to give you the opportunity to study these orbitals and rotate them around at your leisure on your desktop. Okay, and now let's look at the bonding counterpart to that anti-bonding orbital we just looked at. So this one is the two-bladed propeller to which I referred. Okay, and you can see that this orbital has the same symmetry with respect to its nodal properties as a carbon 2p orbital, because it's got a single nodal plane, and on one side all the signs are positive, and on the other side all the signs are reversed. And we have a nice piece of bonding going on there and there when we have this oblique interaction of one of the lobes of a p orbital simultaneously with two of the hydrogens which it sits directly between in space. So there's one of our triply degenerate components of our highest occupied molecular orbital. Okay. And then there's just one left to visualize. All right. And okay, we'll delete that one, and then we looked at our most symmetric and most bonding molecular orbital, and now we're going to go ahead and look at the anti-bonding counterpart of that one. Okay. Each time I move over here. Okay, and so this is clearly a molecular orbital that is formed using some piece of the carbon 2s orbital, and you see that you get a change in sign as you go from carbon to each of the hydrogens, that accordingly the electron density is depleted in the region of space between the nuclei, and that's a characteristic of an anti-bonding orbital. And this one, according to our diagram, in fact, is the LUMO. So as you'll see over here, that was what we predicted our lowest unoccupied molecular orbital would look like. And then up here we had our triply degenerate LUMO plus 1 based on the carbon 2p orbital interactions. So now you can see what these four types of molecular orbital would look like. And now you wonder, just what kind of prediction does this make regarding experimental observables? And so let's look at this picture. This diagram contains a number of interesting features. It is a diagram that plots ionization energy here on the x-axis against a number of different molecules on the y-axis. So at the top you have simply a neon atom. So neon is our noble gas atom that lies just immediately to the right of fluorine in the periodic table. So if anything's more electronegative than fluorine, it would actually be neon, this inert gas that is extremely difficult to ionize because it holds so tightly onto all 8 of its electrons. Does it hold equally tightly onto all 8 of its electrons? The answer is no, because as you scroll across here in ionization energy, you see that its p electrons, its 2p electrons, ionize here, and its 2s electrons ionize way over here. Okay? So the type of diagram I showed you last time, where the 2s orbital, as you go across the periodic table, decreases in energy faster than does the set of 2p orbitals associated with an atom, is expressed in this diagram here, because we have neon, and then we're going across the periodic table. This next molecule is HF, an 8-electron species, and H2O, an 8-electron species, and then NH3, ammonia, the other 8-electron species, and then over here we get to CH4, the molecule that we've just discussed today. And what's very interesting here is that the ionization energies of the molecular orbitals in the case of the molecules and of the atom in the case of neon track very nicely. Here's the molecular orbital that has 2s character of HF, of H2O, of NH3, and of CH4. And it is rising in energy as we go from right to left across the periodic table. And that's because the carbon 2s orbital is much higher in energy than the neon 2s orbital is, for example. And the carbon 2s orbital is contributing to that most bonding of molecular orbitals of the methane molecule. And then there's this manifold here that corresponds to ionizing an electron out of the HOMO of methane. And it's a broadened peak distribution here because of the different vibrational states that the methane can be found in when it, in fact, experiences an incoming high-energy photon that is capable of knocking the electron out of the methane molecule and ionizing it. This is called photoelectron spectroscopy. And you'll be reading about it also in the context of your problem set, because we have a problem that deals with this, and I point you to a piece of your text which covers photoelectron spectroscopy. But the key point here is that if you had all your 8 electrons at one energy, as valence bond theory might suggest for a molecule like this, you might think you should only see 1 peak in the PES of methane, but you see 2. Because methane, the molecule, has 2 molecular orbital energy levels, one of them being triply degenerate. See you on Wednesday.